దుర్గాలక్ష్మి ఒకసారి భట్టాచార్య గారిని ఒకసారి కనెక్ట్ చేయమ్మా.
ఓకే సార్.
సార్ ప్లీజ్ జాయిన్ సార్. ఒక 10 minutes లో జాయిన్ అవుతారంటండి భట్టాచార్య సార్.
I have joined.
Thank you, sir. Thank you.
Yeah, Shavit, good morning. Nataraju here.
Good morning, sir.
Good morning. How are you?
Fine.
So prepared fully?
A little bit.
Okay, nice.
Thank you.
They're all our people only, so don't worry.
Yeah.
Okay?
Yeah, thank you.
Durgalakshmi, shall we start the program?
Yes, sir.
Subramanian garu live streaming అవుతుందండి?
Yes, sir. అవుతుందని చెప్పారు సార్.
Okay.
They're all our people.
Komala madam, please start.
Good morning, one and all. Welcome to one-day national level webinar on science and technology for device fabrication organized by the Department of Physics, Government College Autonomous Rajahmundry. The Government College Autonomous Rajahmundry is a 168 years old college and is the only one government college which has accredited with A+ grade under 2017 RAF. And the Department of Physics was established in 1930 and has given great individuals to the society in various fields. Our department is the second largest department in the college with a team of 24 faculty. Under the guidance of our dynamic principal and the coordination and cooperation of all the members of the department, we are able to step ahead in every aspect. On this occasion of one-day national level webinar on science and technology for device fabrication, I request Joint Director of the CCE, our dynamic principal and the Rajahmundry.
అమ్మ తలపై లైట్ దగ్గరికి సౌండ్ చేయకండి.
It is not audible.
Oh, it is working, sir. Now I request our principal David Kumar sir to give a keynote on this event, sir.
Yeah, very good morning, all the friends.
Good morning, sir.
And I welcome everyone to this national webinar on science and technology for device fabrication. So I appreciate the Department of Physics and Electronics making this possible to organize this webinar. Congratulations to Dr. Vishweshwar Rao and Satyaji, Electronics Department, and Vice President of this webinar is Dr. K. Anjaneyulu. And I welcome the resource persons, friend, colleague, Dr. Rao, Ramchandra Rao, and Bhattacharya, Professor Bhattacharya. Welcome to this webinar. So it is on the eve of Science Day celebrations. So the Department of Physics is organizing this 2 days different webinars at national level, inviting the expert and renowned faculty as resource persons. So I wish all the best, and I declare open this webinar, and this will go all the proceedings of this webinar. will go in a smooth manner and it will be useful to our student community. And as all of you are aware that this institution is now striving hard to implement world-class education. And at the same time, we're also the curriculum is revamping from time to time for better interest of the student community. And also industry mapping is also going on now, because our main future vision is the institution should make the employer choice. So that's our vision of the institution. So towards which we are just striving hard and then try to implement various innovative methods in learning and evaluation processes, also research and extension activities. So the I really appreciate the physics department for the last 1 decade. The Department of Physics is really is a pioneer department. And not only that, it is a unique department in the Government College Rajahmundry, wherein the research activities under the guidance of Dr. Ram, and then Nanoscience Technology Department, and then various programs were taken up and then serving the institution. So I really congratulate Dr. Ram. Now he is the principal, but even then he is the principal. He's coordinating with the research activity at Government College at Rajahmundry. So I wish all the best. I once again congratulate the organizing committee for making this possible, for organizing such a national webinar. All the best, and thanks for giving this opportunity to address at the inaugural session. Thank you.
Thank you, sir, for your valuable suggestions and great talk given about the occasion, and also the vision and the innovative methods which are going to be implemented in our college. Whatever the inputs we have taken, we'll definitely implement in all aspects of the department. Thank you very much, sir. Now, I request the in charge of the physics department and the convener of this one-day national level webinar, Dr. T.K. Visweswarrao, to give the opening remarks on this occasion.
Good morning, madam. Respected President of this national webinar, Dr. David Kumar Rapaka, and Vice President Sri Andra Anjaneyulu, resource persons of this occasion, Dr. Ramchandra Rao and Dr. Bhattacharya, who is from Baba Atomic Research Center, Mumbai. Ramchandra Rao is the principal from Government Degree College, Chodavaram, Visakhapatnam District, AP, and the convener, the previous Sachaji, and organizing committee, and my dear participants, good morning to one and all. It is my privilege to speak a few words in this national webinar on science and technology for modern device fabrication. The Government College Autonomous established in the year 1983, and the Department of Physics is established in the year 1930. UG courses were introduced in the year 1970. This department has 24 sanctioned teaching posts, working with 11 PhD holders. This is the biggest department in physics in the entire AP, offering 7 programs in UG and 1 program in PG. Nearly 1100 students studying with physics background, and we have 2 research labs, namely crystal growth and the nanotechnology labs. The department has very big laboratories and a departmental library and 1 antique lab, which is equipped with 150 years old equipment. The Department of Physics so far conducted many workshops, seminars, summer research projects, orientation programs on national and international levels. So far, the department introduced 3 MPhil and 10 PhDs under the guidance of Dr. Ramchandra Rao. So our principal encouraging our department in all aspects. We must thankful to our commissioner, sir, for giving permission to conduct this webinar on online platform. Also thankful to authorities of Mark for their valuable support. Tomorrow, the department is going to conduct one more webinar on sustainable photovoltaic devices for future world. I hope this webinar will provide knowledge among the science lovers. Thanking you to all. Now I invite Madam. I wish to hand over the mic to Komala Madam. Thank you.
Thank you, sir, for the good information given about the event and also the cause for organizing this event, this webinar, and also addressing the participant. Thank you very much, sir. Now, I request Durga Lakshmi Madam to take over the mic and continue it further.
Thank you, ma'am. It is my privilege to introduce Dr. K. Ramchandra Rao Garu, Principal in Physics, Chodavaram, Visakhapatnam, and also he is a research supervisor. He is the person from Government Degree College who has internationally name and fame. So happy to have one of resource person in our national webinar, sir. Ramchandra Rao, sir, welcome, sir. He got gold medal and first rank in MSc Nuclear Physics and got State Best Teacher Award and IUFF Award from CCE, Government of Andhra Pradesh in 2014. He established 2 research labs in our college, Government Degree College Rajahmundry, Crystal Growth and Nanoscience Research Center, and guiding till now 10 PhD students and 2 MPhil. Now present 2 regular and 2 part-time scholars are working under his guidance. I am one of the scholar of sir. He has collaborated research work with BARC, Mumbai, NPL, Delhi, SSN, Tamil Nadu, etc. He selected Indian prestigious Raman postdoctoral fellowship in 2016 to work at University of Lowell, USA. He has published till now 67 national and international level research articles and 60 national level and international level seminars and workshops, so many programs. Now he will talk about energy materials for device fabrication. Thank you, sir.
So thank you. Thank you, Durga Lakshmi. Am I audible?
So you are not visible, sir.
Yes,
Not
sir.
visible?
Yes, sir. Yes, sir. No. Again.
Sir, visible, sir.
Okay, sir. You are visible.
I guess my screen is also shared. Is it
Yes,
right,
sir.
sir?
Yes, sir.
Yeah. So at the outset, I must congratulate the Department of Physics, Government College Autonomous Rajahmundry, and my heartfelt wishes to our dynamic leader and principal of the college, now Joint Director of the Commissionerate of Collegiate Education, Dr. David Kumar Garu, for providing me the opportunity to participate in this national webinar and integrated approach for science and technology sustainability. And also my sincere thanks to the head of the department, Vishweshwara Garu, and in charge principal, Sri K. Anjaneyulu Garu, and also from 2 to 24, all the members of the Department of Physics. Really, I appreciate your efforts to make this particular national webinar on the occasion of this National Science Day, invention of Raman effect. Okay, then let me start my talk on this energy materials for device applications. Most of the participants are students, I guess. I am going to explain the contents which is relevant to this particular energy materials a little bit of work which is carried out in the laboratory of nanoscience at Government College Autonomous Rajahmundry, and some other applications also. Then first let me introduce this man, C.V. Raman, the great Indian physicist. So there is a connection in between to this Raman to the Department of Physics of Government College Rajahmundry. Why I am telling this, you know, I headed the department for the last 5 years, and I worked there for 15 years as a different positions in that college. And there is a well connecting to this great man to the Department of Physics. What is the connection, first of all? So let me tell you about a few things about this. Monday, means 28th February, the government of India declared as National Science Day on account of invention of Raman effect by the great Indian physicist C.V. Raman. He is the one and only Nobel laureate, and also received the highest honor of the India, Bharat Ratna. Okay, so it is the right platform to explain the connection between the Department of Physics to C.V. Raman. And then now you come to this point here. So Raman further, if you look at the Raman further worked as a physics teacher or physics lecturer at AVN College, Visakhapatnam. Right now I am in V.S. Krishna College. I'm delivering this lecture. There are here also some conducting some Science Day celebrations. As a part of that, I came here to give another lecture here. So Raman further worked in AVN College, Visakhapatnam, and then he taught physics, mathematics here, and he roamed around in this Andhra Pradesh, Visakhapatnam, Rajahmundry area. That is a one thing. And Raman is an intelligent man, man. Why means, see, nowadays, sometimes we are, when we are going through the newspapers, so the boy who completed, at the age of 12 years, he completed his graduation like that. We read the news in the newspapers. But way back you go in 188, that is the birth year of Raman. 1888. So that is the birth year of Raman. He completed his 10th class at the age of 11 years and completed his graduation 15 years, UZ, and also completed his postdoctoral degree 17 years. So that is the history of Raman. See, in this graduation and post-graduation, both these degrees completed at Madras Presidency College, MA Physics, BA Physics and MA Physics. So way back to the history, 1853, the college was started as a Jilla Parishad school at Rajahmundry. In that time, under Madras Presidency, so there were 3 colleges in the entire South India. The one is Government College Rajahmundry, and the second one is Madras Presidency College, and the third one is Government Arts College, Kumbakonam. So this is such a prestigious college, the Government Autonomous Rajahmundry. Connection is, now I am telling you the connection to Raman to the Department of Physics, Government College Rajahmundry. So that means, see, the Raman at the age of,
Sir, your voice is not audible, sir. Sir, your voice is not audible, sir.
Sir, is it okay now?
Yes, sir. Yes, sir.
Yes. So at the age of 18, he completed all the things, and then he went for Calcutta for to work as a financial officer. So that means, but
there is a poor network, sir. The voice is not clear, sir.
He
Sir Ramchandra,
don't
sir.
want to stop his, studies.
Sir, voice is not clear, sir.
Actually, yes. So my signal is good, sir, here. Just look at this one more time. Am I correct? Am I?
No, sir, it is not
Yeah.
clear, sir. It
The
is not.
host muted
Sir.
me. That is the reason I guess you are not hearing my voice. Is it right, sir? Now is it?
No, sir, it is not clear, sir.
Not clear?
Yes, sir.
Anybody other?
సార్ బ్రేక్ గా వస్తుంది సార్ ఇప్పుడు నౌ
jarring voice.
సార్ క్లారిటీ లేదు సార్ ఒకసారి మళ్ళీ జాయిన్ అవ్వండి ఏంటి నాది స్క్రీన్ కనిపించలేదు
Meanwhile, we can make an announcement.
వాయిస్ డిస్టర్బెన్స్ వస్తుంది చూడు మీ రూమ్ నుంచి.
Ask everybody to mute, please.
కదా
సుబ్రహ్మణ్యం గారు మ్యూట్ లో పెట్టండి సార్.
Sir, am I audible now? My signal is full here, sir.
ఎస్ సార్ నౌ ఆడియబుల్ సార్
Yes, my signal is full, but something, disturbance. Yeah, I want to continue. Yes, my voice is full now. Is it right, sir?
Sure, sir.
Yeah. Now, see, I'm introducing the great Indian physicist and Nobel laureate and Bharat Ratna, Raman Garu, CV Raman Garu. So now I stopped at, he's a so intelligent man. So why we call him as intelligent means, see, at the age of 11 years, he completed his 10th class, and 13 years and 15 years and 17 years, he finished all the graduation program. And then, see, the graduation program, during his graduation program, he published an international paper on molecule scattering. So that is his greatness. And after that, he went for Calcutta. And there is Calcutta to work as a finance officer there. And there is one more institution in Calcutta. And he didn't stop his studies there. Calcutta, one center is there. Indian Association for Cultivation of Sciences. That is the place where he worked and executed his effect in 1928. Before that, 4 years of rigorous work with his colleagues. So this is the thing. And then he spent only 200 rupees with a limited equipment. He able to make a discovery and got him Nobel Prize. So this is the history. And then now I am going to give a connection between the government Department of Physics Government College to this Raman students. The next, if you come to this part, you are looking at Raman brilliant students. Is it right? Am I audible, sir? Yeah, Raman brilliant students. So under this, you just look at this. One of the guy here. So this man is a brilliant physicist. In 1928, at the young age, at the age of 20, he went and also joined as a research scholar under Professor C.V. Raman, and who is the alumni of the Department of Physics. This Suri Bhagavantam is a great physicist. After that, he joined the Department of Physics, Andhra University in 1932. So much of history is there, but he's the alumni of the Department of Physics. There's a connection between the Professor C.V. Raman to our Department of Physics, And that's why every year the Department of Physics is celebrating this in a huge manner, and the college is open for all the public, for all the inventions, for all the facilities which the college is having. So that is the history. And also one more thing is there. So with that connection, with that connection, I may be blessed. I blessed, actually. I blessed to have the postdoctoral fellowship on Indian postdoctoral fellowship Raman PDF with his name. Actually, the government of India giving every year Raman postdoctoral fellow with his name to go for abroad and continue their core research and come back and do the work in the respective colleges or universities. So I have enough fortune to have with his name a Roman postdoc fellow. I went for years. So because of all the efforts of my colleagues and me, which is carried out some experiments at government college at Rajahmundry, with the blessing of all the then principals and especially Dr. David Kumar Garu. And then now come to the next point. Now, actually, I want to tell you to all the participants who are gathering here to give a little bit knowledge about the light energy materials, and also some kind of devices which we prepared in association with Baba Atomic Research Center, Mumbai, with chemistry division. So that means, my principal collaborator, Dr. Sudarshan, chemistry division, Baba Atomic Research Center, Mumbai, who has given an opportunity, and we have a collaboration. The Department of Physics have a collaboration with, chemistry division, Mumbai, and we have an opportunity to work on some device application with nano materials. That means nanoluminescence materials. Just I wanna give you a brief idea. So it is not enough to cover the entire topic, but try to understand the essence of this content. Okay, so that means just I want to tell you the nanomaterial, introduction of nanomaterials, and then the importance of nanomaterials in different fields, and where we work and what kind of device we prepared. So this is the thing which I want to explain you within half an hour. Yeah, just let me tell you the sense of the scale. So if size is small, the energy is more, according to the quantum mechanics. One equation is always stressing this point. So I will explain you that. So this is, you just look at, you are looking at here, it is orange, and the size of this is nearly 0.1 meter. So what is, we are all living in this blue planet. The size of the blue planet is 10 to the power of 8 times of this. Okay, now, so that is the bigger size of which we are visually seeing that orange. Then if you come to the down scale, then this is 10 to the power of -8, that is 1 nanometer. So here, so that means above atomic scale, then the matter behaves differently. So that means the different behavior of matter is an advantage for all the scientists across the globe to go for device fabrication, new scientific advancements in this particular scale. So this is the sense of the scale. And then now come to the point, the nano means everybody knows it. The nanomaterials, and then that's why. So the Department of Physics is all the one of the papers. So that means elective and core papers, nanoscience and technology. So the challenge of science is nano, and the future is so tiny. That is the tagline for this. So I don't want to spend much time on this particular topic. Nano, given the sense of nano, is the nano new? I guess no. You just look at This is 4th century Roman chalice. So, Legorgas cup, when you are looking at this, you just look at this. So then means when visible light falls on it, it gives you the colors. So that means nano clusters, and then it lumens. It will give you the luminescence. So this technology, the human 14th century technology hydrophobicity. So
Sir, again, the voice is not clear, sir. Ramchandra, sir.
Hello.
The voice is not clear, sir.
Sir, full signal. Let's check once. Am I audible, sir, now?
Break out, sir.
Sir, one more person, just. Am I audible now?
No,
Sir,
sir.
audio breakout, sir.
Sir, it is jarring.
Oh. Floor also. I am not in ground floor. Is it right, sir? Now, is it audible, sir? Is there any problem?
Slightly
Yes,
better.
sir. It is. Now it is audible, sir.
Now it is audible.
Yes, sir.
So nanotechnology is all around. So that is, you know, so these are some of the curiosity things to get, you know, knowledge about this nanotechnology just for students' sake. And then this is 1 billionth of nanometer. I don't want to stress much on this. And when you are looking at this, then you just understand with this technology, we can prepare very tiny machines. So just you are looking at, so this is the one of the tiny machine. The future is still a little bit ahead of us. It's like, you know, you just world's smallest motor you are seeing on the screen. The motor works on the shuffling of atoms between the two molten metal droplets in carbon nanotubes. So just it is a surface tension driven nano electromechanical relaxation oscillator. That is the name of this. And then you search for the Google and you can learn many more like this. This is one of the invention of these carbon nanotubes and its applications. Just for curiosity, I'm telling this, showing this slide. And then next, there are different methodologies to prepare nanoparticles. That is a big science. But even if I will tell you only one or two sentences. So when you bring down the from bulk to nano, bulk to micro to nano. So when you decreasing the size, then automatically there is increasing energy. And also when you decreasing the size, then the particles which are at in bulk manner, the behavior of electrical, chemical, magnetic, optical, and physical is different. When you decrease the size, then all the properties are entirely different, entirely new phenomenon you get it. So that's why the people are fascinated to go for preparation of nanoparticles and applying these nanoparticles for different fields. Okay. Then now, different kinds of nanostructures is also there. Different kinds of nanostructures is also there. Nano shells, nano quantum dots, and these are all different things. If you want, you can go for different kinds of 0 dimension, 1 dimension, 2 dimension, 3 dimension, different years. The scientists, they work and then they got the different results and they explored it. and then they invented many scientific fields with these nanostructures. Okay, so that is the interesting part here. And the beauty of this is how this particle size is decreases when the energy is increases. Means I'm always, it is my one of the favorite slide to explain to my MSc and BSc students and all others also. So this is very, very important equation for all the students. So particle in a box. So that means particle in a box, it is one of the expression which you get in the quantum mechanics. And then the energy expression when you derive for that particular equation, particle in a box, by applying quantum mechanics, Schrodinger wave equation and all, some boundary conditions, then you will get an equation E1 equal to h cut square pi square by 2m L square. So when you are looking at this E square, h cut square, pi square, L square, almost all, when E and L are inversely proportional. When the length is decreases, energy is increases. That is one of the explanation to understand the quantum mechanics, quantum mechanical background with nanophysics. And also see, this is the quantum dots, gold, different size of gold nanoparticles they prepared here, and then they put in different bottles. So when you expose some kind of radiation over it, and then the same gold particles will give you the different colors because of the size. So that means size is matter here. So when the size is decreases, then the energy will be increases. The energy will be increases. So by that you may get different kinds of radiation here. Okay. So then let me go for the next thing. See here, what I have explained you here, you can see by using the nano science or nano spheres, the scientists, they're able to explain you different size of the particles. They will give you the different visible absorption spectros when you are looking at. So see here, different, so this is hollow gold nano solutions. So when you are looking at hollow gold nano solutions, then the absorption spectra, if you are looking at, so you have different blue colors, pink color, and then green color with different sizes. The sizes and the diameter of nanospheres also they are giving here. According to that, you will have different colors here. Okay, so what I mean to say is here the size matters, and then here, so one material they prepared Bayer Technology Services, and that material here zinc sulfide and cadmium selenide. So these two they prepared, and then they different sizes. So suppose if you have here, here green color, I hope you are all seeing here. And then suppose if it is 3.8 nanometer, and then you have yellow color. And then here another nanometer of size is there, 5.9 nanometer, you have red color. So that means different sizes of quantum dots, that means nanoparticles, then you have different emissions and absorptions. So according to this, we can understand that different size, that means size is matter here, different size of nanoparticles will give you different kinds of emissions and absorptions respectively. And then see, this is the idea, and this is the principle which we use to prepare one device based which is named as electroluminescence device. So that means how we did the device with the help of the bar people, I'm going to explain you now. And then see, one of the most exciting application here I am showing you. So sterilocilia. So this is, you can see here. So this is the TEM diagram. TEM diagram of what means when you are looking at this, the sensory hair cells of the inner ear. So when you are zooming and grabbing the pictures inside our ear, and then you can find the different lengths here. and which is about nearly 200 nanometer thick of these sensory cells, so which are there in our ear. Okay, so C means when the sound waves when are going and touch with this particular hair cells, so inner ear, then you can differentiate different sounds, low, high, low pitch, high pitch, and minimum, maximum, all these kind of things. So that kind of mechanism is already God is given us. So that is we are exploring now, you know, with the help of nanoscience and this thing, that thing. Okay, this is already there in our ears, different thickness of nanometer, nearly 200 thickness of nanometers, different lengths, respond different frequencies of sound, which are there in our ear. Okay, so that is one of the example, you can find it here. And the next thing is the nanomaterials and science and technology is not restricted to only physics, only chemistry, only biology. For it is for every in every domain, making use of the advantage of these nanomaterials and the technology. Okay, there are some modeling, some simulations, many things, material science, electronics, magnetism, optics, in every manner, in almost all the things they are using it. Okay, and then now let us come to the interesting part of my work, and which we carried in the Government College Autonomous Rajahmundry, the materials which we prepared, and then we made make a device with the help of the BARC people. I am already told, and then I'm telling you, explaining you one by one things. So that is especially my domain, my field is optical materials, and to find the optical properties of nanomaterials. That is the thing actually. So that means, suppose if you come to the history of these things, these optical properties and optical methods, when you are looking at this. So blue LED invention and got the Nobel Prize, we all know, and this is a big sensation in the light energy technologies. Blue LED is one of the greatest invention. So the Nakamura, Amano, and Akasaki, so they got the Nobel Prize for the inventing of the blue LEDs with the help of optical properties of nanomaterials. So that is the thing. And the next thing is, for these particular optical properties of materials, nanomaterials, super solid fluorescence microscopy, that is also for chemistry people, they got Nobel Prize for inventing the optical properties of nanomaterials, and also transmission of light in fiber and optical communication and CCD invention. It is also in 2009 Nobel Prize is there for Caillot, Boyle and Smith. So these are the optical properties of these particular nanomaterials are so important. What I'm trying to say is, here, so the studying optical properties and then exploring the things, and by understanding the material optical properties, the people who have got in this particular field 3 Nobel Prizes, 2009, 2014, and 2014. So the great invention for that particular year, 2014, is the blue LEDs. So why the people are interested in blue LEDs means there is a one point here. The one point means, see now the blue LED means when you come to the light technology and light source invention. So 0.1 lumen for watt, just ordinary light. So and then which is illuminated by wick, and then next 15 lumen for watt incandescent bulb, and 17 lumen for watt, these are the tube lights and all, and 200 to 250 lumens which we are taking from blue LEDs. So this is based on gallium nitride thin film based technology. Okay, so the next why the people are inventing still optical properties of nanomaterials and the technologies means the world needs less consumption of energy. So that means, so all over the world, they are working on this particular solid state lighting. So SSL, solid state lighting. So that means the technology which leads us only 2 points. The first point is saving energy spent for lighting. So that is a one thing. And the second one is a reduction of carbon emission in the process. These are the two essential parameters looking all the scientists across the globe for the applications of luminescent materials or optical properties of nanomaterials. So these are the two main points for the scientists, how best we can save the energy on lighting. So that means by consuming the less energy, we have get high luminescence, high lighting. So that is the idea behind the luminescent applications. Okay, so there are different goals: cost effective, longer lifetime, and luminescence efficiency, pure warm white light. These are all the goals for these optical properties of nanomaterials who are working in this particular genre. So that means, say you look at luminescence efficiency, pure warm white light, cost effectiveness, these are all the considerable things. That's why still they are working on this different
Sir, voice is breaking.
No network connection.
Sir, Ramchandra sir.
మేడం సార్ డిస్కనెక్ట్ అయ్యారు, ఒకసారి ఇన్ఫార్మ్ చేయండి.
ఫోన్ చేస్తాను మేడం నేను ఒకసారి.
డిస్కనెక్ట్ అయ్యారు.
Sir is connecting soon, sir.
now?
Sir, you are not audible, sir.
వచ్చినావా రవి?
Sir, am I audible now?
Yes, sir. Yes, sir.
Sorry for the inconvenience. Yeah. Sir, how much time is left with me, sir?
So you can 10 more,
Sir,
you can take 10 more minutes, sir.
10 minutes only. Okay. So I'm sorry. Okay, right. So let me finish my talk at least 15 minutes. Okay, 5 minutes, sir. I request. I require to finish.
Okay.
Okay. So then actually, I would like to introduce the luminescence part. So anyway, I have given a light, thrown a light on this particular part, luminescence. I don't want to go in depth because the time is very limited, 15 minutes. Okay. Anyhow, the luminescence is nothing but it is a non-thermal type of optical radiation, which we all know. For the students, you just remember it. But the beauty of this material is just I am telling you the materials that are able to convert, invisible energies. So like UV, beta, gamma, X-rays into visible light. So this is the beauty of these materials. Those we call them as luminescent materials or phosphors. The process here explained well, and just I've given you the different definition. And then next, if you go for the next slide, yeah, this we all should know. So here you are looking at an electromagnetic radiation and visible spectrum here. And so the UV, violet, blue, green, yellow, orange, red, near infrared, like that. So these are the different colors have different nanometer size length of photons. And then so according to E equal to hc by lambda, you can calculate the electron holes. So here it is. And the beauty of this wheel is you just if you prepare a material, if you expose one kind of radiation over it, and then you can take the complementary color. So that means the opposite color of it. For suppose if you prepare a material of a right size, which is fall in between this, suppose the green, 390 to 575 nanometer range, and then that particular material which emits, absorbs by your nanomaterial, and then it will give you the red color, that is 647 to 700 nanometer range of wavelength. So like that, violet to yellow, orange to blue, like the different colors. So what I'm trying to say is, by using this nano sized materials, and then we can tune the color. That means color tunability is possible, whereas bulk material, it is not possible. Bulk material means only single color or one unique color you will get it. But here, by tuning the colors, you can make different size of nanoparticles. By that you can get different tunable color emitting materials. So there are some physics behind this. How can we prepare the material and what kind of material works for this? What is sensitizer, and what is activator? This is a science. And then just we can go interested students or participants, you can go through what is sensitizer and activator, and different materials works for sensitizers and different materials for works as an activator. And then once if a photon which is falls on a particular material and which acts as a sensitizer and which sensitized to the photon and which is observed and which goes to higher energy levels and come down to the ground level by relaxation mode, and then you can get a luminescence. So this is a small explanation which you can understand. And here the beauty is you can see this material also we prepared here in our laboratory with the BARC people. So see here the zinc sulfide, this is a well-known luminescent material. But the beauty of this slide is you just look at this here. So we are we are making impurities in it. So that means the zinc sulfide, when you dope silver atoms, you expose some kind of radiation, you will get blue color here. And then at the same time, the same zinc sulfide material, if you put copper, then you will have green color. So that means which is depending upon different band gaps. So the different band gap of material, different EVs is getting absorbed and the emission is different. So that is the understandable thing here. The next, we go for in our laboratory, my laboratory work, I am going to tell you how we prepare a materials and how we worked on the SSL, solid state lighting technology materials. So generally in our laboratory, we working on this, we do work on this particular ABO3 perovskite structures, and then nearly 5 PhDs we produce for on preparing different materials. So this is a different kinds of perovskite materials, oxide materials, which are robustic in nature. That's why we choose this. And then a very simple method we took to prepare this particular material, that is a polyol technique. Anybody can understand this, very simple. And I guess with a nearly 120,000, 20 to 30,000 rupees, any person, we can start. This is a simple method to prepare this particular structure of material. So the material cost a little bit more. So that's it. A simple flow chart is here, you are looking, and then just go through the simple procedures, and then you add these things, you will get finally precipitation, and you will get nanoparticles with the different dopants will give you a different band lengths and different band gaps, by the different absorption and different emission. By that you can tune the color. This is a simply flow chart and you can understand it. If you want, I can give you the presentation also. So see, once you prepare the material, you have to go for, whether the material is a single phase material or multi phases are there, with what material you prepared and what kind of phase you got it. So the check is very important. That is nothing but a characterization of your material. So if you prepare a material, different materials, so we prepared here different combinations of materials. This is a one PhD work. See, lanthanum gallite is a well-known material, and we doped bismuth, we doped europium, we doped terbium, we doped bismuth and terbium, bismuth and europium. These kind of different combination, a systematic study, study we carried out. By that we understand the material and its property and its tunability and its color emission. So that is the main intention which I want to tell you all the participants here. So that means, so what is the size? Suppose if you prepare a material, kind of size it is. And then whether if you put terbium or any rare earth kind of materials, if you put as impurities in that material, then whether that material is is there in your final product or not, that also you can check. That is a FESM. And then so that materials, suppose if europium is there, europium is here, and then gallium is here, lanthanum gallate with europium and bismuth, if you prepare, and then EDAX, you will get all the components which in your component, in your prepared compound present or have or not, you can get this data. And then finally, different band gap calculation also possible, but with a very simple mission, that is a UV visible spectroscopy, that is available in our college. And also optical band gap is very simple thing. Even though MSc students, they did projects in our college on this, preparing one material, and with the help of UV visible mission, they calculated a band gap with a simple formulas. So that is one kind of research inclination we are doing in the, that means the people who are working in the Department of Physics, they are taking out this kind of works as a project works. And then see, there is a different emissions and absorptions also we carried out with the same material, and the material photoluminescence emission and excitation is also you are looking at by that. So this is emission spectra, and this is absorption spectra, and this is emission spectra. By that, how much of time this light is emitting, that is depending upon the decay time, that also we have calculated the prepared material. So here we prepared a lanthanum aluminate with bismuth and europium terbium dysprosium with a nano phosphorus. Like, then you have different emissions and different excitations is also possible. You are looking at all these things. So see here, different colors also you are getting by different sizes. Here excited 274 nanometer, and emission is 680 nanometer, like that. What I have shown you, the electromagnetic spectrum, different colors, those are all the things, the theoretical we explain things we observed while studying the photoluminescent spectroscopy here. And then these are all the these are all the same spectra. We have got we worked on different kinds of materials, and we got different spectrums and the respective decay diagrams also. And the energy transfer also we studied in these materials, because it is a nanophosphor materials. Energy transfer means, so see, then lanthanum aluminate, we prepared one material, and then we doped with the bismuth, and means firstly we activated a bismuth with lanthanum aluminate, and in addition to that we put an europium. So that means it is a cross intersection. By that we are increasing the relaxation time. When you increase the relaxation time, automatically you will get high luminescence. So that is the intention behind the co-doping of this thing. That is also one of the procedure we followed in our laboratory. And these are all the things. Then when you are looking at, you just look at this. This is a Cie calculation, that means Commission International Charge. That means color coordinators. I can say in one CIE coordinates means color coordinates. So suppose in different combinations of bismuth you have, so see here, blue to green, so here blue, light blue to yellow. So here blue to pink. So that means different combinations we achieved different color tunability for this particular preparation of material and understanding of this material. This is all okay. Then finally, so I have given a promise that device fabrication, energy material for device fabrication. Out of this, whatever the things you are doing, just it is not for science. You had to expect, or BARC people or any funding agency, they expect from you is some device, some product is needed for any funding agency. If without product, then the funding is waste. That is the idea to fund to your concept. So that means for that purpose, with the able guidance of Dr. Sudarshan and other eminent scientists and BARC, we've take a turn towards for device fabrication. So here electroluminescence. So previously you have learned, photoluminescence. So by exciting photons and UV photons, and you will get visible photon. So that is the relation. But here, so there is a slight change. So the slight change is electroluminescence. So means simply the same thing. You can get a visible light here instead of exposing UV light. Here you are exposing electric field. So, but the thing is, without the thermal energy generation, you have to expose electric field over the substance. By that, you will get visible energy. That process, we call it as electroluminescence. You can do these things in the form of prototype devices. So this is simply you just understand the electroluminescence is simply a radiative recombination of electron and holes. It's like a simple semiconductor. That kind of phenomena, it, and that means all people from 12th class onward, they are learning it. So this is the thing which we are. Sir, am I audible? Sir, am I audible?
Yes, sir.
Yeah. So this is electroluminescence device. Then simply it is a result of a radioactive recombination of electron and holes, such as semiconductor type. And we used here, generally the technology is for thin film and thick film. But in our laboratory, thin films preparation that is a different process, and huge money is involved here. Our proposal is, thick film. So by making powder, this materials, and then you form it a paste with a binder, and then go for applying this electric field. By that, if you get a visible color, that is a device. So that is used in back panels of your car or other. So then that we realized with the people of Bark. So see here, you just look this my slide. So that is the material which we prepared. The structure of the material also I will show in the next slide. So see how this device is working here. You just look at this. Then when I am switching on and off. See, so when I apply some electric field over this particular, the material which is coated over this ITO coated glass, then you will have a luminescence here. So all kind of these things, there are the electroluminescent gauges here. So the simple phenomena is here. You take a silver paste to you just prepare a nanomaterial and you put a binder over it to become a paste. And a flexible PET you take, and conducting a layer is there, and over that you just form a thin layer over that one insulator, barium titanium oxide insulator, and over that silver paste. So that means in between the two electrodes you are putting your phosphor and binder, and one dielectric material is insulator is also for structure. Electroluminescent device preparation is like this. So one is silver paint and a flexible PET. These two acts as electrodes, and then if you give an electrical signal over it, then you will get a light here. See, then with the help of these things, we could able to achieve some blue light. See, we prepared a zinc sulfide with 1% of copper, and we apply certain voltage. By that we can get some blue light here. This is a simple device. We prepared a zinc sulfide material with 1% of copper in collaboration with Bark, the government college autonomous Rajahmundry Department of Physics prepared this device. And this is also large area displays also we prepared with the help of the Bark with the same material. And another material, so this 1% copper, 1% of copper is doped here. Then the blue light with a different size of material. And see why the people are preparing this blue color means The simple thing is, when the blue light is exposed on your body. So the recent studies, why in 2014 they got Nobel Prize invention of blue LED means there are some inventions when the blue light is your BP, blood pressure. So that is a report says, so near 450 nanometer of blue color of light. So that is the research reports. They explained it. So that's why we concentrated this kind of panel displays with the help of simple applying electric field. We are able to produce a light. So which is a very simple and non-thermal, and which is very useful for another project also in the same line, and with a single material without doping of anything. If you prepare a material and which can able to give you the white genre, and we are applying project also my things, then see some material we prepared and we putting some rare earth material and some other bismuth material, these things, one material, two material, like that. No need of putting any kind of other material. A single material, does it give? Suppose if some light is exposed on you, if it gives you a pure white light, that is a new invention. The people around the world, they are working on it, and some interested guys and interested participants, if you want to work with that, and you can also explore the technology. And some other materials also we prepared, and we have seen this electroluminescence light, that is a blue and this is a green. Zinc gallium oxide with manganese doped nanomaterial is also coated with INO, and then we have one more green panel thing you can observe here. So this at this junction, I would like to stop my lecture because time is over. I need to attend one more seminar. I hope I have given a bit of I hope you have understood what my intention behind to explain the energy materials for device fabrication. So you just take a motivation of my lecture is the research is nothing but we need big money, huge money, and huge infrastructure. This thing, that thing, nothing. So my inspiration is only Raman. So he could able to give you a wonderful technology to the world with a cost of 200 rupees. Then with the 20,000 rupees in our college, we explained, we have given a wonderful papers and as well as theses, and research students who are working in that, the research students are also there in the department, because of with simple things and simple research. We could not compare with the bark people. The next speaker, he may give you a lot of things because he is working in the bark, and then he have very good facilities maybe, and he may be giving extraordinary information. But with the limit collaboration, we are doing this kind of things. Thank you for giving the opportunity to share my ideas with you all on this wonderful day. It is a great day for me because I came out of the department. I am giving as a principal to the same department teachers and other faculty members. So thank you, sir.
Please spare 1 minute for questionnaire.
Yes.
Any questions? Any questions from audience?
So I'm
Sir, if I may, I'm Shovit Bhattacharya here.
Yes, sir.
So I'm from BARC.
Yes.
First of all, I should congratulate you for a very good research, and with the group that you are working, it's very highly recognized group,
Yes.
and that's really good. I just wanted to understand one thing, that lanthanum aluminate, when you are talking about doping, so
Yes.
you are co-doping it with bismuth and europium, or sometimes copper and bismuth.
Not copper, sir. We work with only lanthanum aluminate with bismuth as a bismuth activated lanthanum aluminate with co-doping with europium, dysprosium, terbium. That only, sir.
Okay.
Not copper.
It, what sites are bismuth and europium going? Are they occupying the same sites, or they are different sites for that?
as per the interatomic distance, they are inserting the same size, sir, according to the ionic size, ionic radiations.
No, I was just talking about the crystal lattice site. Which, I mean, is it replacing lanthanum or aluminium? Or is it going in the interstitial places?
We guess it is interstitial site, sir.
Okay, thank you. That's all.
I have one question.
Yes.
Nataraju from BRC again.
Yes, sir.
Thank you, Dr. Ramchandra, for your very fascinating lecture on the starting from the connection of C.V. Raman to the college, and also your connection with BRC, and every time acknowledging BRC. I should thank you for that. And my one question is, what is the voltage or current or power that you give for your electroluminescence devices?
Actually, that is huge, sir. That paper I have to check. I need to check, sir. Once.
I think these are battery operated. So 9 battery operated, I think.
These are, sir.
No.
This
the
is
battery will
operated
deliver the fixed thing, but what is the actual device consumption?
Device consumption, I don't have an idea, sir.
Okay, fine. Okay. Thank you.
Any more questions? So other participant can post their doubts on chat box or can email to the Ramchandra sir. He will clarify each and every doubt further. So thank you very much, sir, for your valuable talk on energy materials for device fabrication. You have given a very useful and valuable information about the methods of preparation of nanomaterials, how the size of the particles affect the physical and chemical properties, and the applications of nanomaterials in various fields. So thank you, sir. And I am sure that all the participants have gained knowledge and have got the information about the energy materials for device fabrication. Thank you very much, sir.
Thank you, sir. Thank you, madam. Sir, with the permission of the chair, I am leaving, sir. So,
no, I request.
Sir, waiting.
Okay, sir. Thanks.
Thank you, sir. Now I request Sheikh Yusuf Basha Garu to take it further.
Thank you very much, madam. Sir, audible, sir? Thank you very much, madam. I thank our head of the department, sir, for giving me this opportunity. At the outset, I am very much privileged to introduce Dr. Shovit Bhattacharya, sir. Dr. Shovit Bhattacharya is a scientist working at Baba Atomic Research Center, Mumbai. Sir worked on thin film high temperature superconductors during his PhD. Later on, Sir went to Weizmann Institute of Science, Israel, and worked on freestanding films of piezoelectric materials required for Israeli Defense Academy. After that, Sir joined BARC as K.S. Krishna Research Associate in 2003 and absorbed as a scientist in 2005. Sir's research interests are development of thermoelectric power generators, development of sensors for toxic and explosive gases like H2S and H2 using nanoscale materials, development of Al2O3 based radiation detectors. Sir has one US and an Indian patent along with more than 150 publications in international peer-reviewed journals. Sir has edited 2 proceedings for American Institute of Physics and has delivered more than 20 invited lectures at various platforms. Sir has developed thermoelectric generators for converting waste heat from nuclear reactors as well as radioisotope thermoelectric generators in conjunction with ISRO. Sir has developed and transferred technology for H2S and H2 gas sensors. With this brief introduction about Dr. Shovit Bhattacharya, sir. Sir, we are pleased to hear you on thermoelectric devices, sir. Sir, please. Sir.
Thank you very much. It's a very good, pleasure for me to be able to present here. I must thank the organizers, especially Dr. Rao, who took special care. Maybe I'll stop my video so that the bandwidth is... So,
నాయిస్ మీ దగ్గరే వస్తుంది సార్, మాకు రావట్లేదు.
Some background echo is coming, I suppose. Am I audible now?
Yes, sir.
Yeah. So I'd like to quickly thank Dr. Rao also, who took special care to invite me, and special thanks to Nataraju sir, my senior in BARC, who proposed my name, and that's how I'm here. Thank you all. So with this, I'd like to start my presentation, and let me share the screen. So I hope my screen is visible now.
Yes, sir. It is visible, sir.
Yeah. So I'm again, once again, I'm Shobhit Bhattacharya. And today I'll be talking about development of thermoelectric generators from material aspect to device fabrication. So in this, what I have done is, this is the plan of my presentation. So I'd like to answer some questions like, who are we? So I'd like to introduce very small introduction to BAE, Department of Atomic Energy, and BARC. Then I'd like to answer the questions like, what are thermoelectric materials? Why do we need thermoelectric generators? Where do we use them? How to overcome the challenges that we faced? And finally, I would like to conclude by talking about the ways ahead that we need to take up. So first of all, like my previous speaker, Dr. Ramchandra described about Dr. Raman. So there was, during this era itself, there were a few more brilliant scientists from India. One of them was Dr. Homi Bhabha, who is also known as the father of nuclear program in India. So Dr. Bhabha conceived the nuclear program in India, and he established Tata Institute of Fundamental Research for carrying out nuclear research in 1945. Then after that, he established Atomic Energy Establishment at Trombay in 1954 for including multidisciplinary research programs. And after his death, the Atomic Energy Establishment Trombay was renamed as Bhabha Atomic Research Center. So with this, I'd just like to come to his vision that, India has a lot of thorium reserves, which can be used as a fission material for producing power. So, but we cannot directly use thorium. So he came up with a plan that we generally, the nuclear reactors use uranium to produce power. So, but India does not have a huge reserve of uranium. So we need to come down to thorium, which is which India has an abundance in our country. So he devised a 3-stage program from where we will use uranium as the start product. We will take the plutonium, which is a byproduct of the first stage reactors. Then we will put this depleted uranium and plutonium in a reactor which is known as the breeder reactor, fast breeder reactors, and we'll put thorium again here, and the byproducts will be plutonium and uranium-233. This again, plutonium-233 will be used to generate the third stage reactors with uranium-233, and we'll have the electricity powers. So with that introduction, I'd just like to touch upon the various atomic energy establishments in India. It's as you can see from this graph of our country, it's spread about on almost all the parts of the country. So Atomic Energy Commission has a Scientific Research Council, Atomic Energy Regulatory Board. Then comes Department of Atomic Energy, which overlooks various R&D units like BARC, IGCAR, RRCAT, VECC, Atomic Minerals Division, Directorate. Then industrial units like heavy water boards, NFC, BRIT. Then there are service units like DPS, DC, SCM, and some public sector undertakings are also there, like Uranium Council, Corporation of India Limited, ECIL, NPCIL, that is Nuclear Power Corporation of India, Bhavini, then IREL, something like that. And then there are aided institutes which are DI funded activities like TIFR, Tata Memorial Hospital for Cancer Research, SINP, HRI, IOP, and so on. So this is a beautiful picture of the 2 research reactors that are there in Bhabha Atomic Research Center. The square one, this one is known as the Dhruva reactor, and the dome type is known as the Cyrus reactors. So these are research reactors. They are not used to produce power. They are basically used for the R&D purposes. So now coming to BARC as an organization, Dr. Mohanty is the present director of BARC, and he controls various groups in BARC. So there are so many groups in BARC. We belong to the physics group, and in physics group, again, there are a number of divisions, and Dr. SM Yusuf is presently the group director of physics group, and we belong to technical physics division. And so with this, I would now like to come to the thermoelectrics part. So let me try to answer the question with this, which is what are thermoelectric materials? So what is thermoelectrics? So in 1821, Seebeck discovered an effect where you can, if there is a temperature gradient between 2 metals, like one end is heated and the other end is cool, then you can generate a thermal EMF. So with that effect was known as Seebeck effect. This is the equation where Seebeck coefficient S is defined as delta V, that is the EMF developed across a temperature gradient delta T. So T1 minus T2. So it's written here like this. So this was Seebeck effect. Subsequently, another effect was discovered in 1834, which was discovered by Peltier, where he showed that if you pass a current through 2 different elements at 2 different junctions, one junction will be heated and other junction will be cooled. So this is actually the opposite of Seebeck effect, where this is the equation. Let's not go in the equations. So which defines the Seebeck Peltier coefficient, and then there is a third effect which is known as Thomson effect. These are all basic effects which I know most of us have come through, read across, and we are all familiar with. But forgive me for taking this introduction again, just for the sake of completion. So this is the third effect that is known as Thomson effect. And it was predicted and observed by Lord Kelvin, who is also known as William Thomson. And what it says is that any current carrying conductor with a temperature difference between 2 points either absorbs or emits heat depending on the material type. So here I have added a sentence that is except superconductors. Why superconductors do not show Thomson effect is because the resistivity is 0 for superconductors. So there's no, so the electric or temperature, the voltage gradient is not developed. That's why you cannot use. So now the next question is, what makes a thermoelectric material a good thermoelectric material? Or what is the criteria for calling a material a good thermoelectric material? So there is one term that is known as figure of merit. Figure of merit is defined as Z, and T is to make this figure dimensionless. So T is proportional to alpha square sigma by kappa. So alpha is the electrical conductor, is the Seebeck coefficient, which is many times shown in as S also. Sigma is the electrical conductivity and kappa is the thermal conductivity. So thermal conductivity is divided into two parts, the lattice part and the electronic part. So this is the heart of the thermoelectric devices, where we can see all these things. So thermoelectrics as a subject is very simple, where you can see that this equation is the guiding equation, and we need to remember only and only this equation. That's why I call it very simple. But what we know is that Wiedemann-Franz law tells us that the thermal conductivity is directly proportional to the electrical conductivity. So we want a very high ZT. So what we need is high numerator, but low denominator. So we need very high electrical conductivity, but low thermal conductivity. But Wiedemann-Franz law tells us that that is not possible, because good electrical conductors are usually good heat conductors also. So what we see, if we plot all the parts independently as
ఉండొచ్చు కదా, అవసరం ఉన్నప్పుడు బుచ్చి ఇక్కడ ఉంటే ఆ టీకి చూసుకోవాలి కదా మరి టయానికి వాళ్ళకి పేస్ట్.
Sorry. Should I continue? Is it okay?
Yes, sir. Yes, sir. You can continue.
Okay. Sorry. So if I draw graphs independently of all the components here, then what I can see as a function of carrier concentration, your sigma, that is the electrical conductivity, increases as the carrier concentration increases. Okay, then your thermal conductivity also increases as the carrier concentration increases. But the Seebeck coefficient keeps falling as the thermal conductivity, as the carrier concentration is decreased. So we can see that if we plot everything like this as ZT as a function of carrier concentration, we find that there is a range that is 10 to the power 19 to 10 to the power, in between 10 to the power 20, where the ZT value or the figure of merit is at the maximum. So these kind of materials with this kind of carrier concentration are known as heavily doped semiconductors or degenerate semiconductors. Okay, so keeping this thing in our mind, now we go to thermoelectric device fabrication. So let's say there are basically two types of thermoelectric devices. One is a thermoelectric generator, another is a Peltier cooler. So the thermoelectric generator basically uses the principle of Seebeck coefficient, Seebeck effect, and the Peltier cooler is based on the Peltier effect. So hence the name is Peltier effect. Here what happens in thermoelectric generators, when you apply a temperature gradient, that is there's a heat source and a heat sink, and you place some material in between them, then a current is generated, and if you complete the circuit, a current starts flowing. So this is thermoelectric. Basically, what we are doing is we are converting the heat into electricity. So that is why it is known as a generator. Okay, so this is thermoelectric generator. And what happens in Peltier cooler, if you pass current through similar device, at one end heat is absorbed and the other end heat is rejected. So you can have a cool surface at one end and a relatively hot surface at the other end. So in my entire talk from here onwards, I will be concentrating only on thermoelectric generators. Okay, so what are the main features for thermoelectric generators? So let wear and tear of these devices. So they can be operated for long period of time. They can be operated reliably for a very long time, unattended. So this gives you another thing is like used in places like Siberia where it's extremely cold and very remote locations where you do not have human access. So once you put it up, it will keep working for years together. Okay, so keeping this in mind, I'll again come to the next question. What is the need for thermoelectric generators? So as we can see that if we see, hello. Is it okay? Am I audible? Just tell me if I'm not audible, and you can ask questions in between also. So you can see that around 66% of the heat produced is generally wasted, and only 34% of the heat energy is used. So this energy can be from any source like wood stove, automobiles, factories, power plants, etc. So what we aim is we can take up this waste heat and convert it into electricity. Okay, so for example, taking one example is a car. The car engine produces, this is a typically a diesel engine, let's say. So the amount of energy the engine produces, 30% of it is transferred as torque, and 20% is of that torque is transmitted to the wheels for driving the wheels. 5% is lost as frictional energy, and another 5% is used as alternator, which charges the battery. So apart from this 30%, 70%, remaining 70%, 40% is used up, by the radiator to cool it. 30% heat is spent through the exhaust. Now, for example, if I put thermoelectric devices here on the radiator and on the exhausts, and something around conversion devices with a conversion, very low conversion efficiency also, if I hook up, I can get something around 5% back. So here I can remove this alternator, which is again consuming 5% from here. So I am at a gain of at least 10%. So in this table, I have shown a few heat sources and the amount of heat that is generated here, like furnaces, 150 degrees centigrade, aluminum melting furnaces, you can go up to something around 960 degrees, cement kilns 820 degree. Then there is another component which is known as radioactive isotope decay. So I'll come to this after a little while. Then automobile exhaust, this example I have just shown you. Then solar energy. Solar energy is basically converted using a photovoltaic cell or the solar cells. But again, that solar cell is basically using the photons, the light of the solar spectrum. So what we can do is, in conjunction with the photovoltaic energy, the solar cells, we can hook up our devices and utilize the heat energy from the solar energy. Okay, so that will be an additional energy source to us. Then I'll answer the question, where do we use and what is the motivation that we have for our work in our group. So from here onwards, whatever examples I'll show will be based on the work that we are doing at BARC. Okay, so where are we planning? We have 3 temperature ranges: high temperature range, mid temperature range, and low temperature range. So high temperature range, like I showed you in the previous graph, is the radioisotope or the reactors energy. Then there is mid temperature range, and there is low temperature range, which is between 500 and 900 degrees centigrade, and the low temperature range is lower than 500 degrees centigrade. So why we have divided this into 3 temperature ranges is because every temperature range has a unique set of materials that can be used. All materials cannot be used at all temperature ranges, because some materials are degrade at a higher temperature, some do not work at lower temperature. So that's why we have differentiated it. So coming to the high temperature range, we are working in conjunction with ISRO, and what they have is a radioisotope generator. So what is a radioisotope generator? Let me explain in a few minutes. It is a heat source, which is a radioisotope. Generally, it's like an isotope like plutonium-238 is used, which is an alpha emitter. That is, when alpha is emitted from that radioisotope and it hits a metallic surface, it loses its energy in form of heat. Okay, so that becomes a heat source. Where do we use this kind of energy sources? These RTGs can be used in deep space explorations. In the, for example, you may be knowing that when the solar cells, when the satellites are sent to the orbit, and now we have already sent Mars satellites to Mars. So beyond Mars, the solar flux intensity becomes very less. So for that, you will need a very large size of the solar panels to be taken up in the spacecrafts. So which again, the spacecrafts cannot carry a huge load. So the payload is a restriction. So for those kind of constraints where the solar intensity is less, beyond Mars, let's say, there we need some other form of energy source. So there we use these kind of radioisotope sources. So this radioisotope source gives you a heat source, and then we place our thermoelectric generators here. So I've shown a diagram like this, and the isotope heating sources here. The thermoelectric generator, one end will be heated, the other end is connected to fins. Okay, so that acts as a heat sink, and with this thermoelectric generators, you can connect them and you can power the electronic devices, or whatever, it can be used as a power source. So this is a schematic, this is a prototype design, and here we'll be placing our thermoelectric generators. So this is the device design, and these are the actual thermoelectric modules that we have prepared and delivered to ISRO. So initially we started with this kind of modules, then we shifted to some other updated designs what ISRO is telling us with their feedback, we are always trying to upgrade the devices that we are sending them. Okay, now coming to the mid temperature range. So in BARC, we have a molten salt heat transfer facility at reactor engineering division. And there, this kind of a setup is there. This is a mock-up setup, which will be afterwards used in a reactor for the cooling purpose. Okay, so in the coolant loop. So this is basically nitrite salts, eutectic mixture of sodium nitrate and potassium nitrate is used. And this eutectic mixture can transfer heat up to 800 degrees centigrade. But this mock-up will use transfer heat of to 500 degrees centigrade at a lab scale. So anyway, this is the setup, and what is important for us, we at the top of this area, we have been given a large area which is heated, which is hot. So here I put my thermoelectric modules or devices here, and from top I place either a fin or a water-cooled jacket, so that I get a temperature gradient, and then I take out the output of these materials. Okay, so initially we have placed this kind of 4 independent modules there. After that, we have again redesigned them and made it in a more compact way. And this is now the final assembled thing, which has been mounted there. And so here we have put 2 copper plates, which are very good heat conductors, because so that the entire assembly gets uniform heat from all the parts. And this is another area that we have used. The third temperature range is low temperature range. So here the application is very interesting, and I personally enjoyed working on this, because this is done for self-powered sensors, operating the self-powered sensors at pressurized coolant loop of coolant loops at reactor engineering division. So this is basically a schematic of the nuclear power plants. So it has a core, then there are 2 loops, cooling loops. So the reactor produces heat energy that is used to boil water, and steam runs the turbine, which produces electricity. Now this hot steam is then again condensed back and got into this one, again the reactor, and the secondary loop again cools this, keeps the condenser cool. So these are 2, this is known as the primary loop, and this is known as the secondary loop. So what we do is we put our devices on the hot end of the secondary tube, coolant loop, and using that, because what happens is we have so many sensors here which continuously monitors the pressure and the temperature of these loops. So imagine a condition where there is a power shutdown. So we won't be able to read what kind of temperature, or if the temperature is going up, if the pressures are rising, we will not be able to monitor. However, that is a very, very rare chance. But again, as a safety precaution, what we do is we power those sensors using our thermoelectric generators, wherein we plug them at these hot ends and we generate electricity from this temperature gradient. So these are the devices, and that is the fin. So this part sits over the pipe, that is the tube, and this is the fin, and in between I have my thermoelectric generator. So I can generate electricity, and using this thermoelectric generator, I do not need any external electrical power supply. to run my devices. So even if there is a station blackout condition, that is absolute power failure, my sensors will keep working and telling me monitoring the system and telling me the health or the condition of the system. So that is another very important area where we have started. Now coming to how or what are the challenges and approaches towards realization of thermoelectric generators. So a thermoelectric generator, like I have already shown you some pictures, we have a hot end, that is a source. Then we have a cold end, that is a sink. And in between, we have thermoelectric generator devices. So it contains of N-type and P-type semiconducting materials, which are heavily doped semiconductors. Then we connect them using metal connectors, those two elements. Then between the heat source and the cold end, we have electrical and thermal insulator. Electrical insulator and thermal conductor, so that all the heat is transferred in this direction. We do not want any heat to be transferred from any other path. We want all the heat to be transferred through my devices. So we need a thermal shunt. Then there are a lot of issues that come up, like there are contact resistances. So both thermal as well as electrical contact resistances. So I need all the heat to be transferred from the hot side to this layer to this layer and to be transferred through the material. So there are so many junctions which form and where the heat gets scattered, and as well as in this electrically conducting path, the current gets scattered, or the let's say electrons get scattered. So we need to take up this challenge that the contact resistances are very low, as low as possible, and so that maximum power can be derived out of this. So it has entire fabrication process has can be divided into 4 parts. One is identification of thermoelectric materials. As I showed, that is driven by the temperature range where we work. Second is the ZT, or the thermoelectric figure of merit, which tells you how good a material is. Then we need to fabricate ideal contacts, both electrically and thermal. As I explained, we need very good electrical as well as thermal contacts, so that we do not lose the energy there at the contacts. Then we need to join a large number of these kind of material, these kind of modules in series, so that we get a larger power. And finally, packaging of these devices into a single module. Okay, so keeping this in mind, I'll now come into one example where how we develop a thermoelectric generator. So first step becomes synthesis of high quality single phase material. Here I'm taking an example of lead telluride and tax, that is a alloy of antimony selenide alloy, and then we fabricate thermoelements with metallic shoes, then interconnecting the metals, and finally testing. So I'll show in a little details about all these steps that we take. So this is the synthesis process, where we start from elements like lead and tellurium, and silver antimony telluride is the other. This is the full form of tax. And so this is the process. We vacuum seal it in a quartz ampule, and that inside that you can see there's a black colored bottle, which is a graphite bottle, which is placed inside a vacuum seal quartz ampule, and this is sealed under a high vacuum so that no oxygen can can interact with this material and form oxides, because we need pure lead telluride, PBTE. Okay, so then another thing what happens is this is then put into a furnace, which rocks, that means it goes up and down, so that after at a point where this is melted, the mixture is very homogeneous. Okay, and during that melting, the graphite bottle helps in keeping this material away from contact with quartz, because this reacts with quartz sometimes, and while cooling down, this material contracts or shrinks faster than quartz, and which leads to breakage of the quartz. So we put it in a graphite kind of material. So these are the final products, ingots, that we receive. This ingot is then taken up for material characterization. So there are so many characterization techniques that we use. For example, XRD, EDAX, XPS, something like that, Raman spectroscopy. Then we study morphology and all those things we do. And these are some example of the setups that we have, and we employ very regularly, so that once the material is prepared, we need to know if the material is good enough to take it up to the device fabrication point. So these are the screening level things. So we relied very heavily on these instruments. And once these material have been initially characterized, then we make devices out of it. And this is a setup that we have developed at in-house only, which measures the efficiency of the devices. So this is an example of the property measurements that we have done for let's say lead telluride and tax alloys. So these are the Seebeck coefficient, this is the thermal conductivity, and these are the ZT values. So you can see that my material, lead telluride, has a maximum ZT of something around 0.8 at a temperature of around 600 Kelvin. And tax has a efficiency of around 1.2 at around 500 Kelvin. So after knowing that my material is good, now what I need to do is I need to prepare the thermoelectric thermo elements. So for that, what I do is I compact them in a die set. So again, this is my material. So what I do is, in this die set, you can see there are holes. So in those holes, material will be filled, and these are the plungers, which will help us in compacting it. So this die goes into a furnace, and at high temperature, I put all these materials.
It's 12 o'clock.
Sorry for that. At high temperature, I put all the material in. I use a graphite liner so that it does not, at that temperature, the material does not react with the with my die set. And there are different layers which are being put. Each and every layer has a unique use which is there. So let's say, for example, I need this is my main material which is producing the thermoelectric effect, okay, or the Seebeck effect, or this is converting the heat into electricity. But I need to connect this material to this material through a metallic interconnect. So in order to join a metallic interconnect, I need silver on both ends. Then I use silver strip to join these two thermo elements. Okay, these two pellets. But this and this has, I cannot directly connect silver to lead telluride, because at a temperature, remember, these will be operating at a very high temperature gradient. So here this will be a 500 degrees centigrade, here it will be room temperature. So what happens, silver starts diffusing in lead telluride and it reacts with lead telluride, and lead telluride loses its property. So I cannot use it. So for that I have used iron. Iron is a a layer which acts as a diffusion barrier. So iron arrests the diffusion of silver into lead telluride. But again, my lead telluride and iron, they have a huge thermal expansion coefficient mismatch. So here you can see I've given some example. So there is a huge temperature expansion coefficient mismatch. What will happen at high temperature? This will expand larger. This will expand due to that mismatch of expansion coefficient. There will be a crack. This will open up. So for that we have put in another layer which combines of lead telluride and iron here, so that this expansion coefficient mismatch is gradually reduced. Okay, so for that I have so many different layers. Similarly, in case of this material also. So let me go a little faster. So using those material, those N and P type material, I have now taken up a housing material which is known as zircar, which has a very low thermal conductivity. Why I need it? I need it to make, one, the material of the device a little sturdy. Second, this acts as a thermal as well as electrical insulators, so that all my heat is flowing only through the pellets. Okay, then this is taken up and entire assembly is put in a jig, and then I make contacts, silver contacts with N and P type material and connect them electrically in series. And this is the final kind of product that is achieved. Okay, so after the thermoelectric generator is made, what we do is we characterize it for its output. So these are some results. And see, now we have now produced thermoelectric generators. Now I need to not only characterize it for its output properties, which should be good. I also need to check for its longevity, its life. So here we have tested it for around 300 days, let's say for about a year, and we see that it does not degrade. Okay, that is very important, because my material, my device will be put up in space where there will be nobody to replace the device if it goes bad or something like that. So these are the device characteristics, and I get a conversion efficiency of something around 6%. 6% efficiency, that is 6% of heat that is given as an input, I'm able to convert it into electricity. This number right now may sound less, but in actually, if you look worldwide, this is about the top efficiency that is being received or recorded in this type of devices. Okay, so now again, coming back to that device, what we do is, after I have just shown that we do test for a very long time, now I want to check the interfaces. You remember I have put so many layers. So I want to see if my interfaces are getting intermixed. So what I do is, after the working for a 300 hours, 300 days of working, I take that element, thermo element, cross it, and then I take a cross section and I do X-ray elemental mapping. So what I do is I check if any of the element is interdiffusing or going inside, leaving its place and diffusing in the other thing. So, okay, so that shows me, that gives me a confidence that even after working for 300 days and under a huge temperature gradient of around 500 degrees centigrade, my device is clean. The contact layers are clean. There is no intermixing of this contact. That is why my device do not degrade. So, okay. Similarly, we have made, that was for a temperature range. This type of device was for a temperature range of 500 degrees centigrade. Now I'll show another example of device which we have made for low temperature range, that is something around 300 degrees centigrade. It can work. So that is based on bismuth telluride based materials. Again, device preparation is similar, so I won't go into that. Again, for 100 days we have measured its output, and we have seen that there's just around 3% degradation in this type of devices. And here also we got an efficiency of around 6.3%. So which is very good. Then talking about the third temperature range, that is the high temperature range, we use silicon germanium kind of material. And again, here we have achieved efficiency of around 5%, which needs to be still ramped up. This efficiency we are not happy with. The lack of this efficiency is due to the contact layers. We are losing energy at these contact layers. Okay, so we are working on it, and hopefully we'll be able to resolve it. So now, what are the ways ahead? So this is the last part of my talk. So now what I can do is, I need these devices to be seeing real applications. Remember, these devices are all producing low temperature, rather low voltage and high current. Low voltages means in millivolt range, and few amperes of current is produced. So for any application to take place, we need to boost up the voltage. We need something around minimum of 1.5 volts to drive any electronic circuit. Okay, so what we can do is, what are the areas that we need to work upon is, first is enhancing the figure of merit so that my output voltage VOC is increased. There is another method which is known as segmentation. I'll come onto that in a while. And the third method, which is highly sought after, is using a DC to DC converter to boost up the output that has been produced using these materials. Okay, what existing devices. So again, how to, let's say, efficiency of the device is now dependent on the ZT, that is the material efficiency, as well as the temperature gradient. Okay, so theoretically, if we see, if we get a temperature difference of around 500 degrees centigrade, and the ZT of the material is something around 1, then effectively we should get an efficiency of something around 12% efficiency. And similarly, if efficiency of the ZT of the material is let's say around 5, we can get an efficiency of around 35%. This is all theoretical. Okay, but rather ZT at a ZT of 10. But right now, whatever material we have ZT a figure of merit something around 1. Okay, those are stable materials. Yes, we have also made materials which have a ZT of 2, but and I'll show you one example. Using those kind of materials, we could give or switch the efficiency, the conversion efficiency, by 2 times. Okay, from 6% efficiency, we could achieve 12% efficiency. Okay, so that is there. So, so theoretically speaking, there are scope where we can improve upon. So internationally, ZT of around 2 is achieved, and these are still, we wish, these are all on our wish list, that we have material with very high ZT value. However, so how can we increase the efficiency? First thing we can do this is the ZT, is increasing the numerator or decreasing the denominator. Okay, so that's what I've written, increasing the numerator. Numerator is known as power factor, or decreasing the denominator value. So we can increase the numerator by various methods. Okay, I'll just skip this part because that is okay. But importantly, as during my initial this thing, I told that the thermal conductivity consists of two parts, the electrical as well as lattice part. And electrical is connected to the electrical conductivity also. The thermal conductivity is connected to the electrical conductivity. We cannot, if we reduce this, the thermal conductivity electronic part, we'll reduce the numerator value also, that is the electrical conductivity. So we can focus only on the lattice part. Okay, so lattice thermal conductivity depends on the specific heat, the mean free path, and the average velocity. Okay, so what we can do, this is material dependent, these two parts. So what we can do is we can reduce the mean free path. So that is where we start playing. Okay, so now the material in these days have been divided into three parts: first generation, second generation, and third generation. So first generation materials have a ZT which is less than 1%, less than 1. Second generation is between 1.3 to 1.7, and third generation is high, that is around 2.2 or higher. Okay, so now taking up these materials, we have started to think how to increase the ZT of the materials that we are producing. For example, silicon germanium, because we are still struggling with the conversion efficiency in silicon germanium. That's why we started focusing on the material property itself. So what we did is by ball milling, like my previous speaker already told you that nano materials play a brilliant role. So we also looked at the material with the nano scale, and we introduced various defects in the material itself during the process, and we were able to enhance the ZT value. Okay, so we were able to reach the ZT value of around 1.8 from a value of less than 1. Okay, so that was a big achievement. And then another example was we introduced nanoparticles, additional particles like yttrium silicides in silicon germanium alloy. Okay, using that also we could enhance the ZT value, and by reducing the thermal conductivity. I'll quickly go through these some examples. And another one was titanium oxide was introduced in silicon germanium, where we could decrease the thermal conductivity and hence enhance the ZT value. Okay, so then there is another type of material. This is a very new material where we could scatter the phonons at various length scale, or rather, let's say phonons have different wavelengths. Okay, so we can scatter phonons of different wavelengths using different scattering centers. So phonons with wavelengths of around 1 to 10 nanometers can be scattered by atomic disorders. Okay, higher wavelength phonons can be scattered using line defects, point defects. Then mesoscopic phonons can be disturbed using mesoscopic scales. Like I have added two types of material here. So at the grain boundary, it will be scattering. So I used my knowledge of different wavelengths of phonons and different type of scattering centers that I can introduce to scatter a very large number of phonons. Because previous examples I've been always telling you that I have put in a nano dopant, or I have introduced one defect. So I have been able to scatter phonons of a certain wavelength only. Now, in this type of engineering, this is also known as materials engineering, what we have done is we have introduced defects or scattering cross centers at different wavelength sizes. Okay, so with this, we could get a very high ZT value. So initially the starting material has a ZT of 0.1, of 0.8 and 0.1, but here we could enhance it to 1.4. Okay. Similarly, by doing various other methods like intercalation in titanium diselenide, we have this is a layered structure. We have, what happens is in between two layers we have put in copper ions. Okay, copper atoms that acts as a scattering center, and with that we were able to enhance the ZT values. So we have this is more of an advertisement kind of slide for us. We have worked on various material, out of which few of them are reported as the highest achieved ZT value materials that have been developed in our lab, and a few publications are shown accordingly. So that was all from our lab, materials from our lab. Now we do collaborate with others also, like this example where we have collaborated with Professor Kanishka's group at JNCSR. They have created a material which had a ZT of around 2. I was talking about a ZT2. We have fabricated a device out of it, and in that device we could achieve an efficiency of more than 12%. So I was telling you that we have
sir, try to finish it within
in one, in 2 or 3 slides I'll be finishing it up.
Thank you.
Yeah, so the efficiency we could enhance by 12%. No, we could double the efficiency. So another approach which we took is segmentation. Okay, I will skip this, but another approach, we could again enhance the efficiency by 12%. Okay, so then as we know that there are these type of devices are low voltage but high current devices, but for practical application you need at least 1.5 volts. So we need to either combine a number of PN legs which becomes cumbersome, or achieve a DC to DC setup. Okay, so we saw at a very large number of literatures, and then we finally made our own booster circuits, which are nothing but boost up, which will boost up your initial millivolts to volts. So you can see if we get a voltage of something around 300 millivolts, we can boost it up to 10 volts. So that is what we have done. And with this, I'll conclude. And you can see that in our lab, we have been working on various devices with various efficiencies. We could improve the efficiency of a single material itself, and we could improve the efficiency using a segmented approach also. Okay, so these type of materials have been used, and with this I would like to end. And this is my group. He's Dr. Ajay Singh, he's our group leader. This is myself, this is my colleague Pritam Sarkar, Ranita Basu, Dr. Ranu Bhatt. So I would like to thank them all, and other colleagues from TPD, RED, and also EMED, because initially Dr. Nataraju's group was also from TPD. Now they have gone to EMED, another division. So I can still consider them as TPD members only. They have been helping us in this one. Professor Kanishka and his group from JNCSR and ISRO. So this I conclude. Thank you And I would like to answer a few questions if students have something. Thank you.
Any questions from participants?
Again, I will ask one question.
Yes, sir.
Dr. Shobit, I know they are not connected, they're well apart.
Mhm.
How do you compare the efficiency with SOFCs, solid oxide fuel cells?
So solid oxide fuel cell efficiencies are higher. But the problem with the solid oxide fuel cells are you'll need continuous, I mean, how we, in support of our devices, what we can say is that our devices do not need any human interface now.
Okay.
But solid oxide fuel cells, you'll need continuous input of at least the gases.
Okay.
So that's it.
Okay, thank you.
Sir, I have one question.
Please, sir.
So as you showed your present PPT, the initial said that there is a radioisotope heat source. So in a closed chamber, so as you need the one junction is hot and another should be like cold. So how you maintain the temperature difference in those closed radioisotopes?
Yeah, so the radioisotopes basically has, they are basically alpha emitter sources. Okay, now we are talking about particularly the radioisotopes. Okay, so they are alpha emitters. So the alpha particles, whenever they are emitted out of the material gets heated up. Okay, this is an exothermic reaction, and that heat is transferred to my device, and that is the hot end. That heat from the radioisotope itself is the heat source for my device, and we use fins because that will be in space, and space has a very low temperature, -4 degrees or something like that. So that gives me a good temperature gradient. I hope I'm able to answer your question, or was it something else?
Yeah, I got the answer, sir. Now I understood.
Okay.
Sir, this is Komal Lakshmi. One question, sir.
Yes, ma'am.
So what the difference makes between using of a graphite disc and graphite liner, sir?
Yeah, so graphite liners we were using, graphite disc and liner we were using during the hot pressing of the thermoelements. What happens, my die is made up of stainless steel. Okay, and what we do in a hot press is that we put all the material, this is like just pulverizing, but at a very high temperature. So we put the material, we apply a huge load at a very high temperature. So the sintering is done at the time of pulverizing. But now what happens, at this high temperature, the activity of the material is a little high, the chemical activity. Okay, so due to that, if I don't put a graphite liner, this material will interact directly with the stainless steel or the walls of my press, and it reacts. With that reaction, it will get attached to the die, and I'll not be able to take it out. So in order to avoid that reaction, and you know, graphite intrinsically has a lubricating property, so that helps me in getting the pellets out of, I mean, pellets pressed without any interaction with the stainless steel of the die material.
Sir, thank you, sir.
Yeah.
Any more questions?
I have one last question. As I see in your presentation, there is a use of like chalcogenous materials like TMDs, tellurides. So as we know, telluride materials are toxic. So how you will reduce the toxic levels of those materials?
This is a very good question. What we are doing right now is we are working on different materials which are chalcogenide free, like half oilsless are some examples. We are trying to avoid lead also, lead free material also we are using. But anyway, right now, whatever materials we are using, we are taking all kinds of precautions, like we are working on glove box kind of setups, where the material fume does not comes to us, and all the work is done using protective gears. So that's how.
Okay, sir.
Yeah.
Any more questions? Okay, thank you, sir, for the valuable insights on thermoelectric devices. It is very informative, starting from what, why, where, how, and need of developing thermoelectric generators and the energy materials. The inputs you have given will be helpful for pursuing further research in our career. Thank you, sir. Thank you very much.
Thank you very much.
Now, OTA thanks by Sri P.V. Satyaji, sir.
Hi, very good afternoon to one and all. It's a great privilege to me to propose vote of thanks on behalf of the Department of Physics and Electronics, Government Autonomous College, Rajahmundry. First of all, I am very much thankful to Dr. David Kumar sir, Principal of this college and Joint Director CCA Amaravati for his keynote address in this webinar, and Sri K. Anjaneyulu sir, Vice Principal, for his continuous support in conducting this event, and HOD, Department Head of the Department of Physics, Dr. T.K. Vishweswara sir, for giving his inaugural speech, letting the young minds, and for the resource persons. First of all, I'm much thankful to Dr. K. Ramchandra Rao Garu, Research Advisor to the Department of Physics, Government College Autonomous, and Principal, Government Degree College, Chodavaram, Visaga District, and giving a picture on energy materials for devices fabrication, for considering the students and research scholars. And very much thankful to Dr. Shoit Bhattacharya, scientist, F Technical Physics Division, Baba Atomic Research Center, Bombay, for his relevant lecture on thermoelectric devices. And also thankful to the organizing committee, the Department of Physics and Electronics, and technical supporters. And finally, I'm requesting HOD sir to conclude the session. Sir Vishweswara sir, please.
Thank you very much, sir. Satyaji, sir. See, I feel it is a great privilege to me to say a few words at the end of this webinar. I must be very much thankful to V. Nataraju sir, who is the head of Physics Division, and LM Pant sir from BARC, and the resource persons, and and our principal sir, and vice principal sir, and my staff supporters and the technical assistants, and my dear participants. So I conclude this program at this time. Thanks for the participation. Thank you, sir. Thank you, sir. Bhattacharya, sir.
Thank you very much, sir.
Thank you so much, sir. Thank you. Right, sir.
Madam, let us end the session.
Please end it.
Let us leave.
2.5 minutes.
Hello, sir. There is a session will be over or not?